Exercise 1.2 from Paolo Aluffi's Algebra Chapter 0. This exercise asks us to prove that the equivalence classes defined by a relation tilde on a set S form a partition. So what is an equivalence class again? Every element A of S defines an equivalence class. Namely, it is defined as the set of all elements B of S that are equivalent to A. So it is a subset of S of all elements B that are equivalent to A. Now, what is an equivalence relation again? An equivalence relation is a relation that is reflexive. Every A is equivalent to itself. Symmetric is if A is equivalent to B, then B is equivalent to A. And transitive is if A is equivalent to B and B is equivalent to C, then A is equivalent to C. So, and now we need, using these three properties of tilde, we need to prove that the equivalence classes are non-empty, disjoint, and that their union is S. So how do we know that these elements are non-empty? Well, for every element of the partition can be described as an equivalence relation of some element, right? So for every element, for every element A of the partition, or we don't know if it's a partition yet, but of P under S, right, the set of equivalence classes, there exists at least one A, element of S, such that A is an element of the equivalence class of A. Because, and we know this, because A is always equivalent to itself. So this follows from reflexivity. Now, how do we know that the elements of P under tilde are disjoint? So suppose we have two elements of P under tilde, the equivalence class of A and the equivalence class of B. Man, that is ugly. And suppose that we have an element C that is an element C of S that is an element of both the equivalence class of A and the equivalence class of B. Then from this we can conclude two pairs by definition of equivalence classes, right? So from this we can conclude that C is equivalent to A and that C is equivalent to B. Now using the symmetry of tilde, we can conclude that A is equivalent to C. And then using transitivity, we can conclude that because A is equivalent to C and C is equivalent to B, we can conclude that A is equivalent to B. So therefore, the equivalence classes are the same. So the contrapositive is that if the equivalence class of A is different than the equivalence class of B, then it cannot be that there exists a C in their intersection. Namely, they are disjoint. And then for the last property, the elements of P under tilde form the elements of P under tilde, the union of all of them forms S. Well, so this we need to know two things for this to be true. Namely, there are no more elements in it, right? So the union of all the elements of P under tilde isn't bigger than S. We know that because the elements of P under tilde are subsets of S, right? This here defines a subset because we take elements from S. So so the union of all the elements of P under tilde certainly is not bigger than S. And we know every element in S is accounted for because tilde is reflexive. So it follows, so the fact that all elements of P under tilde, the union of all of these is equivalent to S follows from the fact that they are each a subset of S, and that every element in S is accounted for. Namely, for every element in S, there is an element in P under S for which it is an element. So therefore, we have proved these three properties. And that is the end of the exercise.